Hi folks, this video is going to be going over fission, fusion, and nucleosynthesis. So we're first going to start with fission, and the idea is we're building off of the concept of nuclear chemistry. And so remember, we're looking at just the nucleus here. So in the process of fission, fission involves the idea of taking a very heavy radioactive substance such as uranium-235 or plutonium-239 and shooting a high-speed neutron at it. What ends up happening is this causes a disruption within the strong force as well as the repulsive force, imbalancing that proton to neutron ratio, causing the nucleus to become unstable and causing it to split into two different new elements. So as we can see here in the top right, we've got krypton 92 and the formation of barium 141. And with this, we also see extra neutrons that are released in order to balance out that proton to neutron ratio, plus a crazy amount of energy. Now, to give you an idea of the energy, 1 kilogram of uranium, which is approximately 2.2 pounds, will release the amount of energy equal to the explosion of 20,000 tons of dynamite. That's a pretty large amount, and when we look at the idea of 1 ton of TNT is equal to approximately 4 times 10 to the 9th joules, that's a crazy amount of energy. And here's the thing. A nuclear fission reaction, what we do in like a nuclear reactor, is a controlled chain reaction, as opposed to a nuclear weapon. A nuclear weapon is not going to be controlled. And so when we look at it, and this idea of this controlled chain reaction, a chain reaction is just that. When one of the neutrons hits one of the nuclei, it causes it to split, and then more neutrons are released, and those neutrons hit more of the larger atoms, such as uranium-235 or plutonium-239, causing it to get bigger and bigger and more, causing more and more energy. And so we end up with this concept of splitting the atom. That's what fission is about. Now, I would like us to take a moment to watch this short little video.
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements, such as krypton 91 and barium 142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amount of energy in the form of heat, light, and ionizing radiation, an atomic explosion.
So this gives you a little more perspective about what a nuclear fission reaction is, okay, in the idea of
nuclear fission is the splitting of a heavy element's nucleus to...
Okay, so I wanted to discuss the concept of does a nuclear fission reactor look like. So in a nuclear fission reactor, what it starts with, number one, is there's a containment shell. The purpose of the containment shell is to make sure that if anything bad were to happen, it would be contained in this vessel. Now, one of the things I wanted you to look at is the reactor vessel itself. I would like you to notice that it's in the color of yellow, and it is self-contained. So the idea is that we have within the reactor, there is water, and that water is heated up under pressure. And the way it gets heated up is by having the uranium rods and control rods. The control rods or moderator rods are the ones that actually control how many neutrons collide with the uranium, so that we can adjust the temperature of the actual liquid inside there. That liquid, that water that's in there, is being superheated and actually will provide enough energy to cause water in the first chamber with production of steam. That steam will then go up and turn a steam turbine, which then produces electricity. That steam then needs to be condensed, cooled down, and put back into liquid water. So you can see how the nuclear reactor never really comes into contact with the exterior water. And that's on purpose to make sure that if there's any type of leakage, we don't have any problems. So this is the controlled reaction. The uncontrolled reaction would involve a nuclear weapon in which you would actually have an uncontrolled reaction of the splitting of the atom. And that's what most of our nuclear bombs are like. Now, we're going to look at the opposite effect of this, and this is called nuclear fusion. Fission is the splitting of atoms. Fusion is the combining of atoms. And so this involves combining very light nuclei, usually in the form of hydrogen, and these hydrogens fuse into the form of helium. So we can see the process here, and no, you don't have to memorize the process, but we can see that we have hydrogen 1 colliding with hydrogen 1, and it's producing hydrogen 2. That hydrogen 2 then collides with hydrogen 1 to form helium 3, and then helium 3s can combine in order to form helium 4 and then produce 2 hydrogen 1s. Now each step of the way that produces energy, and we can also see that it produces a new substance we haven't talked about, which is a neutrino and a positron. Now these processes take place in all stars. Fusion is where it's taking very light elements and fusing them into heavier elements. Now, we see this only in stars because of this reason. In order for nuclear fusion to actually start, there needs to be a tremendous amount of gravity and a ridiculously high temperature, on the order of 5 million to 10 million degrees Celsius to even get it started. So you can see how this would be really hard to do here on Earth. However, we've been trying, and most recently fusion has been achieved on Earth, but not for a long duration of time. The biggest problem is again because of the high temperatures that it creates. It's also difficult to contain those gases, and so they often use magnets to do that. But there was a major breakthrough on December 5th of 2022. We ended up with actually producing a fusion reaction that produced more energy output than what we put into it to get it started, which is the first of its kind. If we're able to sustain this and do nuclear fusion, there is the potential for an endless fuel supply. So eliminating all of our issues with the idea of generating electricity using fossil fuels. Now, the reason we're going into this is because of the concept of nucleosynthesis. Nucleo, we're focusing on the nucleus, and synthesis means formation of, so the formation of nuclei. Now, the reason why we're focusing on this is because we want to know how all of the elements in the universe formed. And in order to answer this, we have to look actually to the stars, because stars get their energy from the process of fusion. And when we fuse elements together, we're creating new elements. And so here I want to kind of give you kind of the life cycle of a star. How does it all begin? So stars start their lives in what is called a stellar nebula, what some people would call a stellar nursery. Where all the pretty stars are made. So stellar nebulas are nothing more than just a conglomerate of gas and dust in the universe. Now what ends up happening is that there's some kind of force, whether it be an explosion from a dying star or something else, and causes the particle matters to start to collide and congregate. When they congregate, if they have a sufficient amount of gravity and bring themselves closer and closer together, they get bigger and bigger and bigger and bigger. These collisions will eventually form a tremendous amount of heat from friction, as well as more gravity, because the more mass you have, the more stable, the more mass you have, the more gravity you have. So the formations of stars actually start when there's enough sustainable fusion reactions taking place. And that happens at approximately 10 million degrees Celsius. Now, as for the mass, we're not quite sure where that is the starting point or end point. However, when the star does form, the densest material gravitates towards the middle. And I know that when we look up at our sun, which is a form of a star, we tend to look at it and it looks the same throughout. However, our sun actually does have layers in it. we do actually have a core to the sun. There is a radiative zone, which is where radiation comes out of it. There's a convective zone in which gases are moving up and down because of their difference in density and temperatures. And there's also the photosphere and chromosphere. So our sun is kind of like an onion. It's got layers, just like you. Now, depending upon the amount of material that the actual sun has in it, within it, and the star and its temperature will determine how long it exists. Our sun, our star, which is the most important one that we're going to be focusing our attention on, is estimated to live to approximately 10 billion years. And right now it's considered to be at its middle age. It's approximately 5 billion years old because we know that the existence of our solar system is approximately 4.6 billion years old. Now, at some point, our star will stop producing the energy it needs. And that's because the star will no longer be able to create fusion reactions. And the reason this happens is because of the fact that it just runs out of fuel, meaning lighter elements. And so what I have here is a diagram of a life cycle of a star. Now you can see that it starts in a stellar nebula. Now, depending upon its mass will determine whether it becomes more of an average star, which our sun is more of an average star, or a massive star. If that average star is to start losing its ability to do fusion, what ends up happening is it becomes a red giant and eventually will form into a planetary nebula, and its end result will be a white dwarf. Massive stars, on the other hand, will form into a red supergiant. They will eventually supernova and will either form into a neutron star or a black hole. Now, the inability to fuse lighter elements into heavier elements causes this imbalance with the pressure of gases in the star along with gravity. During its main sequence where it's doing fusion, the pressure from the gases and the gravity are balanced, so it stays in a complete balance with itself. But eventually, the gravity decreases and the pressure increases. That's what causes the red giant phase, or the super red giant phase, is that the gravity decreases, causing the star to eventually reach a point at which the gravity can't hold it together anymore, and it will either form into a planetary nebula by ejecting its outer atmosphere, or it will supernova, where it actually collapses in on itself and explodes. But this all depends upon its mass. Now, our sun, all right, our sun, which is kind of, I hate to say it, folks, it's an average star. It's not massive. It's not small. It's just kind of average. If we were to put it on a grade, it's like a C-. It will only be able to fuse up to an element as high as oxygen. And that's because it just doesn't have enough mass. It doesn't have to do with the temperature. It has to do with the mass. Now, most elements formed from oxygen up to iron are thought to actually be produced from stars as much as 10 times greater than the mass of our current sun. And then elements, all the other elements past, and for some reason, and here's the thing, for some reason in iron, they don't understand why it is, but once we reach iron, that is where no fusion can occur. We don't know why. We don't know why we can't fuse iron into heavier and heavier elements, but that's the max that we can get. Okay? And if you look at this diagram right here on the right hand side, this is showing you that a supergiant, like let's say our sun is a supergiant, it will actually be able to reach out to the edge of where Jupiter is located. All right, that's how big it will get. And here's the thing. The core, if it's a supergiant, which again, our sun will not get that because it's an average star, it's not a massive star. All right, it will be able to fuse up to the iron core. But once it gets to that point, all right, there is no more material for it to fuse, and what we end up with is a giant supernova that occurs. When that supernova occurs, all the elements greater than that of iron and nickel are formed. So we're talking about all the elements, even elements we have never discovered, well beyond element number 118, oganesson. All right, so I've got a short video I want you to watch, all right, on this concept with two very excited scientists, let's just say. Here we go.
All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. The star begins its life made out of hydrogen and helium mostly, about 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spin.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel this stellar furnace, and so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing's blowing up. And you've made a supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium,
indium,
niobium, molybdenum, technetium,
strontium,
rhodium,
lutetium,
antimony,
ytterbium,
tellurium,
thorium,
iodine,
radon,
xenon, cesium,
francium,
barium, lanthanum,
tellurium,
cerium,
indium,
actinium,
xenon,
thorium, protactinium,
cesium.
uranium. Done.
So as we can see here, all of the elements that we have here in this universe were formed from stars. That is the key to the idea of nucleosynthesis. All right, so technically we have all been born from the idea of stars.